So this is an assembly project that we do in the parametric class. And this is actual project. This is what I use in my machine tools class. So everybody, this is one of the projects in machine tools. So they kind of see it multiple places. And so in machine tools, everybody builds a vise like this. And then in CAD, they kind of redraw it and model it and assemble it. And since they're familiar with it, they kind of understand quite a bit about it, and we can really focus in on just how the whole assembly thing in parametrics works. So I expect them to give me just about the same thing I gave them. So I want a assembly view. I want an exploded assembly with bill of materials and ballooned out. And then I want individual drawings of all the pieces, parts that go with that, fully detailed out. And something like this, I would ask the CAD class to start adding some GD&T where it makes sense, because these parts have an actual purpose, so it's a lot easier. You know why these holes are here and what's important about them and why they need to be perpendicular or what have you. So I'll have them continue to kind of experiment with that. So those are the parts. Can you see my inventor screen?
Absolutely.
Okay. So there's a couple of different ways to approach assemblies, and that's changed over the years to some extent. For this one, the way I start off is I have them draw the individual models to each one of these parts, and then we go into an assembly drawing, and we assemble the pre-made models together. But in actuality, where industries went and what we do in later assemblies is we do everything in the actual assembly drawing. So that way we can create interrelationships between the parts, and we don't have to worry so much about what some of the different dimensions are and things of that nature. But for the first one, I have them do the individual parts. So we'll kind of look at it both ways here a little bit. I'll just use this one assembly as an example. So what I show them, or what I show them is that some of those parts that I just had up on the screen aren't all that different. So if we're going to do these as individual models, as soon as my software gets loaded up here,
Evening, gentlemen. Sorry I'm joining you late.
That's all right. How you doing, Ted?
Okay, just got stuck in traffic coming up from Cincinnati, so. But I'm here now.
All right.
Good to see you, Ted.
So in this first part, I'm not going to go all the way through these. I'm just going to give you a flavor for it, how we approach this. And I'll demonstrate this up in front of the classroom so that they have some ideas here what we're looking for. Oh, I guess that one's already there. Put a couple of dimensions up here. There we go, we're fully constrained. We'll get that to extrude out here. It should be 1.25 inches. Let me put a couple of holes in here. In Venner, we put points down first, and then we put holes on top of our points is the easiest way to accomplish it. I know SolidWorks does it a little bit differently, and not sure about Solid Edge's workflow for this, but it's probably very similar. Well, I kind of lost that dimension somehow. There we go. So this is going to be a threaded hole, and it's also going to have a counter bore on it as soon as my thread data pulls up. My computer is really old. I was just in a meeting today to get new computers, so it's another month away, but I'm trying to nurse this one along. So this is a half-inch thread, half 13. We'll go right-handed, full thread depth, and then the counter bore. It's kind of a non-standard hole, and that goes, how deep does that go? 1/4 inch. All right, so we got our 2 holes in there, and there's some other features on this part. There's an angle back here. I'm not going to put the angle on right now, but I'll try and explain to the students this part is very, very similar to another part in this vise, so there's no sense in reinventing the wheel. We'll go ahead and save this one. I'll just call this jaw 1 for now. I'm not even sure where this is going. And then I'm going to do a save copy as, and I'll call it jaw 2. And let me open up jaw 2. So here's jaw 2. So the other part that is related to this one, first of all, my holes have same holes, only they are left-handed threads instead of right-handed threads. So we'll just make that change in this jaw. And the outline's a little different. I'm going to come in and alter this one. This one actually gets some 45-degree angles on it, so I could use a chamfer for this, but I'm not going to. I'm just going to put these in here. And now that I'm doing this, I'm kind of noticing I put my holes at the wrong location. So I'm going to have to go back and change those. You ever been up in front of the classroom and things just don't work for you and you get those little beads of sweat going and you wish they did?
About every other day.
Yeah. Things that should work don't always work.
Whenever it's technology involved, you sit there and, okay, well, this was working a minute ago.
Yeah. So we're on a cut. I must not have the end point of that line latched onto that line completely. So let me cancel out of this, go back into that sketch, see what's going on here. Says it's already there. That one's latched there. Well, today, just not going to like me.
You just hope you have enough credibility built up, you know, with the stuff that is working. Right.
All right, so there's a 45-degree angle. Yep, I'm going to force that other one to go on because it's kind of annoying me that that didn't go. There to there. Put a dimension in here. See, why is that endpoint not attaching to that line? That's what I don't get. Now we got it. Cut. All right. And as I said, I put those holes in the wrong place, so I'm just going to go in and I got to change one dimension here. It should be 1/2 inch. There we go. So that one's looking pretty good. Let me go back to that jaw 1 and do those holes. I'm just running off the tree right here, but in other assemblies, we will discuss the parameters page where all your dimensions are listed as parameters and how you can export those to Excel and then interlink that Excel spreadsheet to multiple models so that if you change one dimension, they all change. Not going to do that this instant, but that is something that we do kind of play around with on one of ours. There we go. So that's all working pretty good. Need one more here of these kind of standard jaws so I can get my assembly going. So let me build that real quick. This one's an easy one. It's just a rectangle. And I'm just going to put 2 holes in this one. That's all we need. And we'll move on to the next part kind of quickly here. My horizontal constraint in there in a couple of dimensions. We'll have this. Make this one jaw 3. Well, I already got one called jaw 3. We'll call this one jaw 3A. All right, so we've done a lot with extrusion, so there's a shaft that goes with this. Let me kind of bring that up here real quick. So in this assembly, there's a shaft. And so this one we're going to do the revolve with. Just 1 second, gentlemen.
No worries, Shane. We know how this goes.
Yeah, students. All right, I got it taken care of. So in this one, this would be a revolve. And build this real quick for my revolve. I'm going to switch my formats here. Right there, that's what I wanted. Put a center line in there. Grab the collinear constraint and start getting this constrained down. Oh, that one's already in there. You get some equals constraints on here. That's equal to that. That's equal to that. I think that should do it. Start adding a couple of dimensions here. It should be 7.38. Should be 1 inch. To adjust my geometry here a little bit, kind of bring that back in. And that should be 1/8 of an inch. Since I put a center line in there, I get an actual dimension when I click on it. I'm sorry, an actual diameter. So that should be 0.5. That should be 0.615. And then that should be 3/8. There we go, we're fully constrained. So we're going to revolve that one. Found everything, so that's a good looking part. Put some chamfers on here real quick for my threads. We'll just go with the defaults right now to get this accomplished. Put some threads on there. We'll do this one first. Half 13, right-handed, class 2A fit. That one looks good. Left-handed for that one. Yeah, that's a good looking part. We can use that one. So I'll save that. Get a new assembly drawing going here. So Ted, I'm not sure when you joined us, but I was discussing that for this first assembly, I kind of have them do it a little bit more traditional way by building the individual models and then bringing all those models together in one assembly view and assemble them together. But in other assemblies, we would kind of build it all in the assembly drawing where we can create the interrelationships between different parts and make sure everything's lined up so that if one part changes, the other part changes with it and all of that kind of good stuff. But so we'll do a little bit of that, but just going the traditional route here to start off. But draw one in here. Get draw two going. All right, 3A. And then I need, where do my shafts go here? There they are. So when we start assemblies, once they have all these parts built, we'll kind of put them together like this, or I'll lead them through putting them all into one file, and then we're just going to play around with the constraints a little bit in class. So I'm going to talk about all these different constraints to some extent. So in Inventor, my make constraint does 90% of my assembly. The angle constraint is there. Use that at times. And then I have a tangent constraint, a insert constraint when it's just real straightforward, round pin and a round hole. And then I have some symmetry I can build. Two different solutions for especially the straight mate constraint. There are motion constraints. These will apply to some assemblies that work well with this, especially when we get into some of the unknowns where we're actually designing something to solve a problem. So if motion comes into play, that's great. We'll do that. Otherwise, we'll just simply talk about it in class and kind of take a look at it that is possible. Then there's some transitional constraints that we can apply, but for right now, just the mate constraint. And starting off, I would just have them make these parts together, not how they actually go together, but just exploring what one flat surface to another flat surface does. And then looking at some of the different solutions, so how when I pick these two flat surfaces, how if I do the flush or the mate option, how that changes. Spend a lot of time talking about degrees of freedom, that the more constraints you put on here, the fewer degrees of freedom the object has. And let me latch that one part down. It always annoys me when I got a floater out there. So I want one thing that is grounded here. And so as I apply more constraints, I lose my degrees of freedom. And I also try and really reinforce that these constraints, let me say the constraints that we add are what would cause these objects to take their position in real life. So when you assemble this together, what causes something to be where it is? That's the kind of constraint that we want to apply to this. So I'm going to get rid of some of those constraints that I just put on there because they were just as examples. So we'll spend a little time with that. We'll mate different things together and just explore some of the constraints. But Inventor does have this joint constraint where I can, a little bit more intelligent relationship definition. Sometimes I don't even go into this because it's really just the idea of the constraints and how we assemble things together. The excuse me, the joint constraint kind of does some things for you, and that's great. I think it works well, but for understanding, I kind of start here. I'll have them explore this a little bit in some other assemblies, but really I don't force them to use it, just because you don't know what version of software they're going to use, and you don't know what whether it's going to be SolidWorks, Inventor, Solid Edge, or Pro Engineer, whatever it is. So things are going to change between now and when they actually hit their career. So really just having a good basic understanding of how things go together and how these constraints work with each other is the goal. So in putting this together, to center line of the hole to the center line of that hole, and kind of talk about how that's different, then they have to be careful, because if I do the center line of this, if I'm not precise in what I select here, there I'm getting the center line of the hole, but here I'm just getting the center point, and that's a totally different kind of animal. So visually, if you're not paying attention to what you're selecting on the screen, you're not going to get the results that you want. So we'll spend a little time with that, and get that in there. And then to finish this, I'm going to pull those out slightly here and go back into my constraint, and I'm going to orbit around here. And when this actually gets assembled together, what's going to stop this shaft when it goes in the hole is when this shoulder comes in contact with the back of that counter bore. So that's the constraint I would have them add, or ask them to add, or think about at least. They're going through this. So get the back of that counter bore to that one. There we go.
You show them 3D mice?
Yes, I do.
Okay.
In a grant that I just got, I'm going to have space mice for all the computers in there, but not there yet. But that's definitely something that's commonplace in industry. And
yeah, I fought for them. I got 24 of them for my lab.
Have they worked out pretty well in the classroom?
They have, yeah. And I mean, it's funny, back at GM, I remember those were, they were more than $1,000 a piece back, 20 years ago. But now they're less than like $75 a piece, which is, it's still a little pricey, but not, it's still within range.
Have you dealt with how you're going to keep them? Like that's I'm going to get them, but my fear is that they're pretty locked down. So
we're currently signing them in and out every day. I mean, with the I keep telling them, look, guys, this is a little bit more money than a mouse. If you really want one of these and need to, talk to in my case, I'm like, talk to your parents. If this is something you really want to do and you really want to have this thing, outside of using the software, they don't really do a whole lot.
Right.
And I tell them that because, I tried to get one a number of years ago and install it with games and all this. It just doesn't work. They're just not the driver support. Right. So I kind of speaking from experience there, it's one of those, I tell them, if you really want one, we'll find you a way. We'll talk to somebody. We'll make it. We'll see what we can do to make it happen.
Right.
But I've had pretty good success. I've kept them all. Now it's the first year, but yeah, they're pretty easy to. We're checking them in and out still.
Right. Yep.
Yeah.
That's probably going to be the case. So I have a rudimentary assembly going here, and let me get out of my assembly or my constraints there. So don't have this locked down all the way. So let me go back into my constraints. So I think it was Ted who had asked about if I do any motion. So on this first one, what I'll show them is that I can put a constraint up there, and then that constraint I can alter its offset. So if I want that open an inch, I can open it in an inch, and I can also drive that constraint constraint. So I want it to start out at 0, and I want it to end at, I think I have 4 inches of motion there. Oh, a little bit too much. So they can animate it somewhat, and you can record that into a movie, which if you're trying to communicate to somebody how your assembly is going to work, just a couple of simple drive constraints, you can get quite a bit done when it comes to that. Change my delays, and I can slow it down and all that good stuff. So we'll talk about all of that in class. Let me open that up slightly. Open it up a little more. All right, so I have a couple more parts that I need here, so kind of quickly, let me get one part up here, and then we'll explore some different areas. So I need a steel jaw plate in here. And as I'm going through this, one thing that we never touched on is I do have them assign materials to their objects, to their models, and then in their title blocks, I request to know the mass or the weight of everything that they are modeling, so that would hold true in the vise too. Just haven't kind of touched on that in the class at all. Going to be.
Do you make them calculate it by hand too?
No.
Okay.
No, I want them to like me.
That was the project I made them do some of that this year. They found it really, I mean, they still talk about that, but knowing whether this thing is right, how to analyze it. That used to be a big problem when you'd have double geometry, or you'd have things that didn't, that weren't whole solids and all that kind of stuff that happened a lot with older software. Knowing if something looked right.
Right, yeah. So even in the CAD class, I try and encourage them that, if you want to know the area of a circle, please just draw it in AutoCAD and ask AutoCAD the area, or the area of any shape. So as they go through physics and math, tell them, once you know this software package, you need to use it to your advantage. So whether that be a solid model in Inventor or AutoCAD or what have you, like you have this huge advantage over other people by knowing the software, and you should take full advantage of that. So just wanted to get some holes in here real quick. These are going to be through holes. Wow, this is taking a little bit to call up. There we go. Normal fit should be fine. All that works. There we go. There's some, well, we'll go ahead and do it. There's some dimpling that goes on here. And the way I handle that, put a hole point in there, kind of zoom up to this. Dimension that real quick. Same as that one. So how we actually dimple these vice jaws in the machine tools class is we just drill small holes all the way across the faces, and we happen to use a CNC for that because I believe there's like 740 little dimples in there, and that doesn't go too far on a manual milling machine. So they're about 50 thousandths in diameter, and they're only about 20 thousandths deep. So that just kind of breaks the surface tension a little bit, so the vise functions better. But I'll have them use a pattern to put those dimples all the way across their part. And a couple of things you could do, I could have, let me go back to that sketch, I could have patterned this hole point, and because there's a pattern feature here in my sketch plane, but I rarely do that. I prefer to have a finished feature and pattern that. Just works a lot better. So if I'm going to pattern this little hole right here, set up my directions, reverse that, and those holes should be 70 thousandths apart. I have another direction here. Those are going to be 70 thousandths as well, and then just have them kind of explore how many they're going to need. 30 isn't going to do it. Looks like 50 went too far. 48's probably going to be about right. Yep, 48 across, and then do I have 20 down? Oh, no. 15, how about 16? Yeah, 16, nope, 15's it. So there, that's kind of what the dimpling looks like in the pattern feature, and that's how we actually produce that. But what I'm going to do is that all those little surfaces, those are just going to be a memory hog. And so for right now, I'm just going to suppress them. They're still there, and I can unsuppress them when the time comes, but this will allow it to run a lot faster. So we'll just call that part 4. I'm going to go through and close some of these parts down. Close my models down. My assembly, you bring in that part 4 real quick. Need 2 of those. Strain those. All right, so to get these centered on my aluminum jaws here, because I don't have holes in my aluminum jaws yet, they're going to be coming, but I really encourage them to work a lot with planes when it comes into some of the more difficult assemblies. So if I want these jaws to be centered on, these jaw plates to be centered on these aluminum jaws, so I'll show them that they can, first of all, edit their parts in the assembly, so I don't have to leave the assembly to edit that. I get ghost images of my other parts there, but I can go ahead and I'm just going to put a mid-plane in here between that surface and orbit around here, that surface. We'll save that, return, and then in my jaw plate, I'll edit that one in the assembly and put a mid-plane in here between there and, can I get that one? Come on. There we go. Save that one. And then use those mid-planes that I have in there in my constraints. There we go. So now that jaw is centered perfectly. I need to go into this one. Get a mid-plane going. There we go. So those mid-planes will keep my jaw plate centered. And I encourage this because now this will comply with design changes that if we make something longer or we edit, excuse me, edit the size of different parts, I get some design intent going here. And then as we talked about, for these holes in these parts right here, I'll just edit those in place now that I have my jaw plates at their location. So I'll go in and edit that one. And what I'm going to do is a new sketch on the front of that. And then I'm going to project the holes from my jaw plates. So I got some ghost images going there, but from those kind of ghosted jaw plates, I just projected their holes there. And then let me get back to my straight on view. And I'm going to latch some points right down on the centers of those projected holes. Finish that, and I will put in a hole feature. It's going to be threaded. Actually going to be the number 10, 1024, straight hole, full depth, distance goes through all. So there, now I have that part edited. So like I said before, we would do that from an assembly from the get-go, creating the parts here in the assembly and interrelating them. In Venner, when that happens, you get this little symbol over here in my tree showing me that jaw 1 has become adaptive now, so that if I go back into my jaw plate and I change the location of those holes in the jaw plate, the holes in this part are going to change with it. So that's a concept that I try and get through to the students, that continue to create intelligent models that are going to easily adapt to design changes and altercations, because that's really the name of the game. They get so involved in just getting the part done, and they end up, oh, I was too early on that. They end up not building models that adapt well. So always try and encourage that.
Shane, how do you check that, though, on your end? How, I mean, you can kind of give them that, but how? I can't imagine the process, how you would check that.
Right, you go through all the models. No, I do not.
Wow.
So maybe one assembly, I'll have them package that up and send it to me, but I'm pretty straightforward with them. I tell them, look, some of you are going to get great jobs, some of you are not. And this is your opportunity. So there's no second chances. Once you leave here, you're not coming back, and you're not doing this over again. So it really becomes up to them to want to do this. And if this isn't something that they want to do, that's fine. They just need to figure that out. So I kind of give them a pep talk and kind of explain to them what's on the road ahead, and it's really up to them to reach for this or not. So that's pretty hard.
Well, and if they can design efficiently, that's where they can really make money off of doing 3D design.
Right.
It's really a support skill in most of the industry, right? You have some people that just design, but those guys are good. You better believe it.
Right, and who's going to keep their job? Like when you're competing against the person sitting next to you day after day, and it comes time to let somebody go, well, the person that creates models that drives everyone up a wall, that's the first person to go. I tell them the same thing in machine tools. So we run a manual machine tools. We run a CNC and the whole gamut of stuff. But in one semester, I explained to them I'm not trying to make machinists out of anybody. So for the mechanical students, one of the main benefits of taking a machine tools course is you're going to be better at designing parts. Understanding how parts are made is just a big part of creating or designing parts that satisfy a problem or present a solution, but they're also easy to manufacture, cheap to manufacture, just very makeable. And kind of tell them the same thing. Look, if you're the person in the cubicle next to you, if they're designing parts that solve the same solution and they cost half as much to make, well, guess who's going to stay employed when they do this? So I also tell them in the CAD class that most employers that I know of, if CAD's going to be a part of your job, they sit you down in front of a workstation and have you model some parts or create some drawings for them, and they watch you. They give you a time limit, and they're watching what you're doing and how you're doing and whether you're using the software intelligently or not. So it kind of all comes back to them. I've never been one big on grades. Grades make no difference to me. I mean, you got an A, you got a B, you got a C, whatever it is, we have to assign the dang things, but you know, this is all for your benefit, so you have to want to do it.
Yes, indeed. It very much depends on the context. I can see where your background as a machinist really, this really lets you expand and really lets you talk to this stuff.
Mm-hmm. Yep. And
from a real knowledgeable standpoint.
Right. Yep, that's true. And it's true in all the classes. I tell them, you know, this is a tool in your toolbox, and for a lot of subjects, this is not, you know, this subject may not be your main focus of your job. So I said, take hydraulics, for instance. You could hate the subject of hydraulics. You could hate it with a passion. Now, that doesn't mean that when you leave here and you start your job that your main focus will be about hydraulics. But whatever job you get, you're probably going to have to know a little bit about hydraulics. At least know when people are lying to you, that this will work or this won't work, or this is why it's not working, or this is the problem. And for CAD, it can be the same way. Not everybody likes CAD. And for sure, not everybody is good at it. It's just not in their nature. But you still may need to know something about it. So.
Hey Shane, at this point I gotta head out. I got my other class starting here in about 5 minutes.
Okay.
So I just gotta walk in the room, but they're checking people in. So it was great for you to run these classes. Appreciate all you've done here. And yeah, no, very much thanks for doing all this.
All right.
It's a lot of work.
All right. You have a good day, Mark.
Yep. Take care.
So we will place some content here real quick. Need to find the one I'm looking for here. Can never find my oh, that one will work just fine. It does not want to find that hole. Not the hole that I want it to find. All right. Well, if my computer wasn't so old, it would automatically recognize that conical shape there and select the correct size screw for me and put it in place. But it's just not going to work with me today. So, wow, I found the bigger hole. What's up with that? Oh, nominal length. I was looking at the wrong thing. Well, I didn't put it in there perfect, but we could constrain that the rest of the way. So we'll add some fasteners. The other thing in Inventor that, not in this assembly, but in other assemblies that we go through, let me close this gap and I can show you real quick. So if I close that, it wasn't constrained in there at all. But we'll go into some of the design areas so you can do bolted connections. It wants me to save this real quick. But basically I can pick where I want to start. My bolted connection. I need a linear edge. So we'll just go there, some distance, there, some distance. Pick my termination. And then it puts holes in all the parts, and I can add fasteners that go in those holes. So that kind of does everything at once for you. Puts the holes in for the fasteners, and then puts the fasteners in themselves. So in other assemblies, we'll get into this, and I'll have them use this as well. Not going to put all the fasteners in. There we go. We got the fasteners in. All right, so that's kind of the assembly in a nutshell. We do different things with this and different assemblies, but that's kind of the nuts and bolts of it. Does that seem reasonable, Ted?
Yeah. Mm-hmm. When we do it, we start out, I think, probably much like you do. We do a lot of the basics. In fact, their first assembly that they have to do is just on a block design, and the pieces are all squared out, and basically it's a mate flush exercise, but we emphasize the 6 degrees of freedom and how they have to restrain a thing to assembly. And then later on, when we do some of the more advanced modeling, that's when we really get into the bolts and things like that.
Right. Yeah, I'm kind of throwing everything at this one assembly, so for sure we keep this one pretty simple just for their first go around. I want them to have a success. The one thing that I've been toying around with trying to come up with, and I just haven't, is a good design of an assembly that's already done that they have to go in and make altercations to, so that you kind of have that. There's been some design changes made to the assembly or to the individual parts, and you've never seen this before, but it's your job to go in and make the changes that an engineer requested. That'd be kind of a different experience. I just haven't come up with a good assembly for that.
I do a basic jeweler's vise and get them started off the drawings so that they have to go from a drawing to a 3D model. And then about halfway through, I'll hit them with the guy came back and decided he really doesn't want this one, he wants this other one, and let them modify off of that. But I haven't ever given them a full assembly and then just asked them to make changes off of that. But that actually is probably a pretty good exercise with them, because that happens quite a bit.
It does, and then everybody has their own little techniques on how they create models and what they do. So
I've also found that my students have a weakness in the model menu. And I try to tell them, if you really look at the model menu, you can tell how the parts were made, you can tell how the assembly was done. And so that might force them to get into the model menu and decide how they want to adjust their work.
Yep.
So I'll have to look at that. I think that might be a good exercise to try to put together this year for them.
Yeah. I think it'd be worthwhile. So real quick here, this is the exploded assembly. It's just a different file. So we bring in our assembly and then start pulling that apart. Can specify distances and all that great stuff, and start bringing parts out. And so we'll go through this, and it's really pretty simple. There's one tweak components, and then you can animate that, so you can show it going together, kind of the way you took it apart. But I am surprised that this hasn't caught on more, or hasn't become more prevalent, because I know Autodesk was working on it, and I know SolidWorks was working on it, and they had apps for the mobile operating platforms where you could create these animated assemblies and then download them to your app and see how things were supposed to go together or even come apart, which would be huge. Like, you know, the next time you go to the store and you buy a gas grill and you get those dang paper directions that really make no sense whatsoever. That if you had an animated 3D model of, you know, this part goes in slot A and there's slot B and these bolts go in here. And then when you think of the industrial maintenance, you know, if new equipment came with a 3D animation of, like, how do you get to some internal component, what has to come off first, what has to come off second, and in what order, and what it looks like, and it would just really open up a new world for 3D modeling, but it just has not become commonplace yet, and that always kind of surprises me.
Yeah, we do the animations, but it's like you said, it really you don't see it a whole lot. Like, we'll do the exploded views and pick up the parts list off of that, and sometimes I'll have them try to do an assembly guide and recommend they use an exploded view with the trails on so they can see where the parts came from. But you don't see the animation picked up outside of classes much in the real world.
Right. I think that's going to change.
I hope so. It'd be nice.
Yeah. But it'd save a lot of time. You don't have to have maintenance people standing at the broken machine wondering, how do we get to this, whatever it is. So real quick here, I'm going to see if my Autodesk 360 or Fusion will fire up. I haven't started this for a couple of weeks, so we'll see if this works. Sometimes they push down new updates, and my computer isn't the most, does not have the most horsepower in the world. So, have you looked at any of the online kind of CAD programs?
No, I haven't. I've been so embedded into Autodesk here at school, and with everything else I'm doing with my robotics team and stuff, I just don't have enough time to play.
Gotcha.
And I would like to, but I don't. And my wife says that's the true sign of an engineer when you complain that you don't have enough time to play with CAD programs.
Right. Yep. Well, I think this has a lot of potential. It's still maturing, and it's maturing for Autodesk, and I know it's maturing for SolidWorks as well, that they have their own. And I'm not sure what the other software companies are doing, but I don't think we're going to see any less of this. If anything, we're going to see more of it. So.
Yeah, I went to play with the Google one time, wasn't impressed, and basically just stopped.
Yeah.
Figuring I was wasting my time because of the capabilities.
Right, yeah.
Didn't seem as well.
It's pretty weak. I got to remember my password. I can't believe how many passwords you need in this world. And then I've got one, I think it's the Board of Regents, and that password, it's got to be unbelievably long, has to have an uppercase, a lowercase, a number, and then a non-alphanumeric character. So basically, every time I log into the system, I just request to reset the password. Like, there's no way I can remember a non-alphanumeric character in this big, long string. It's just ridiculous.
Well, my middle son is a computer science geek, and he's working for Tata's right now. And he just came out and said they're getting into the security, and they're actually coming up now with a method where they say that it's actually more secure to do passwords that are 4 words and put together. And, disjointed, but 4 words that are easy for you to do. Because he says the real long ones where you throw in the characters and the symbols and everything else, the cracking codes have gotten so good at breaking those down that the actual 4 words are starting to be more secure and harder to break. And so I thought, well, that's kind of interesting, because every time I go to reset my password, they tell me I can't use words.
Yeah, they don't catch up real quick sometimes. And I think we're almost loaded here. Are you able to deal with computer upgrades in the classroom fairly well? Like, do you
No.
get...
I got to get all my upgrades in usually at the beginning of the school year. Most of our programs are run through our server here. So, like right now, I'm on 2012 for Autodesk.
Oh, okay.
Primarily because we switched to a new school building, and then we switched tech people in and out. Because the school doesn't really hire them as tech people, they hire them as almost like normal laborers, so their pay is not that great. So as soon as they get certified and stuff, they typically leave. So what we'll do is I'll try to hit the tech people up over the summertime. So this summer I'm planning on upgrading to 216 and go bring everything up to 2016. But usually I get all of my software upgrades at the very beginning of the year and go from there. And we have quite a few different programs we run for the different engineering courses we teach. So it gets to be a bit of a challenge. Plus, the one thing I don't need is unstable software in the middle of the school year.
Right. Yep. Yep. So they just switched my lab to a virtual network, and no, it's not all it's cracked up to be. I can see how the virtual network, when people are doing, when they're surfing the web or they're doing Microsoft Office products, like if you think of an English class or a math class or whatever, I'm sure it works just perfect. CAD, it ended up taking way more resources on the server end than they ever expected it to take. Took a way more high-dollar graphics card on the server than they ever expected it to take. And it's still, the main problem is the mouse tracking. So it turns out, like in Word and Excel and even the Internet on a virtual network, you don't notice that your cursor lags your mouse. That's not exactly where you think it is. In CAD, you notice it straight off. That it's like you're trying to push the cursor through mud. And one of the main things we found was the actual mice make a difference. So which mouse you're using can slow the system down and speed the system up. So we've had to explore different mice that work better and try and get that, but I haven't been real happy with it. So
we found out the hard way that the working Autodesk off of a server, if your lab is laptops, you start to get all kinds of interface problems. But if they're desktops, you had none of that.
Gotcha.
And our initial concept was to have a lab with a bunch of laptops so students could move them and connect into wind tunnels and other things that we run for other courses, and basically have a portable station that they could move with them to the different equipment. And that didn't work very well. So we're all on desktops now.
Yep, we're all on desktops here too. So I was right. There was an update waiting for me, so it's almost complete here. It's worth waiting for. Looks like that last 2% is going to be the biggest for 2% of the whole thing.
You know, I always love it when they get to 100% and you still sit there for a couple minutes waiting.
Right. So while we're waiting on this last 2% or whatever it's doing, maybe it's getting ready to crash. One of the reasons I wanted to show you this is you'd asked about animations. I've been able to do some really cool animations in this software for my CNC class. So simulating tool paths and having the end mill in there and having the end mill move around the part and remove material, or at least simulate removing material. They did a nice job. They do it in a storyboard fashion. Okay. So, man, you can zoom out and zoom in and rotate your part and then record that into a movie and an MP4 and just really get some nice graphics going that really render pretty well. So the other nice thing about Autodesk Fusion is it'll take almost any 3D file format there is. I haven't found one that you can't load into it. So it doesn't care whether it's SolidWorks, whether it's Pro Engineer. I use GradCAD a lot, and the file types in GrabCAD can vary wildly. And no matter what I pull down off GrabCAD, when I put it in Fusion, it brings up the model without any issues whatsoever. So their ability to translate is extremely well in this.
Probably at 98.1 by now.
Yeah, I know. If I would have been thinking ahead, I would have done this earlier today. But I never thought.
Well, see, that's the problem we have with Fusion here too. Once we do try to bring it up, it just seems to take forever to come up.
Usually, if I don't have an update, it comes right up. But this update's crushing it right now. So. Well, we're not going to spend the whole evening watching my 98%, but at the very least, I'd encourage you to take a look at it or another look at it. And I think, given a little time, this is going to be the what's coming in the future. So I don't think we'll ever lose the Inventor or SolidWorks running on a hard drive right on your desktop. But this is going to make more and more incursions into what we do and how we do things. So. Unless this comes up in the next few minutes here, I was going to call this a class. I've kind of went through everything, and if we went any farther on Thursday, I'd just be making stuff up. So.
Yeah, I think I'll play with Fusion here a little bit this week. As you brought it up, I'll take another look at it and go from there.
Okay.
Now, I told you my son was computer science. He was when he was going to University of Cincinnati, he worked with Siemens on his internship, and he did actually develop a phone app for them that interfaced with Inventor. And they were doing it for a company where most of the design work was done at the desk, but their engineers in the field wanted access to the files and be able to make small design changes based on what they were observing in the field. And, so I'll have to ask him what media he actually did that with, but I know it was a phone app that was being developed for phones and tablets for field engineers.
Okay. Yep, I think it's coming.
Oh, it's coming.
Yeah. I did see on what was it? One of the football games. Was it Patriots using Microsoft Surface tablets to show the players the next play and game, and those things locked up about halfway through the game, and they couldn't use them. So doesn't always work as planned. Well, it said it was restarting, but I don't know.
Yeah.
All right, I think we're going to go ahead and call it a class.
Well, I do appreciate what you did. It gives me a little bit more solid feeling about what I'm doing in class, and it's given me a couple of things I want to look at improving and updating for some of my students. But I also think that my students are in pretty good stead when they'd walk into your classroom.
Yeah, and that's nice.
Which is my big thing is, say, are you guys really ready to walk into that next classroom?
Right, yep, that's nice to know. You kind of need that confirmation that you're doing the right thing. So.
Well, unless you talk to people that are in the next classroom, you really don't know what they see and what they look for. So,
right.
And that was a big advantage to this course.
Okay.
So I thank you for that.
All right, well, you're welcome.